So this is going to be a little lecture on ideal integral compensation. So we've learned thus far how to control just barely by changing the feedback gain. But as we learned, there can be performance issues with that. One of those performance issues can be that we would like our closed loop dominant poles to be somewhere that's not on the root locus. That's one possibility. We're not going to deal with that one today. The other possibility, performance-wise, is that we might have some steady state error that we'd like to get rid of. And that's directly what we're going to focus on with this lecture. And we're going to mitigate that issue by using ideal integral compensation, which gives you a PI controller. Okay. So in this section, we learn controller design with the following aspects. So ideal control, pure integrator. It's active, meaning it would be implemented in active circuits. We're going to use cascade compensation with a forward path compensator, and we're going to be trying to mitigate steady state error. So we're doing steady state error compensation. When steady state error, when studying it, we discovered that the more integrators in open loop transfer function, the better the steady state error. PI control is all about including integrator compensation to a proportional controller without affecting the transient response. Okay. So we would like to affect steady state error but not transient response. Later we'll deal with how to design for transient response specifically, but for now we're going to try to leave it untouched, the transient response, or hardly touched is going to be more like it. So here's the plan. Include an integrator, which is just a pole at the origin. So put it in the controller, and include a nearby zero to counter the pole's effects on the transient response. So the integrator alone actually drastically changes the root locus. And so we can't just pop an integrator in there and expect that the transient response is just going to be fine. In fact, the transient response is going to change drastically. Sometimes it could even go unstable. All kinds of things can happen. So we are going to try to minimize our effects on the transient response by adding a zero nearby, not right on top of, we don't want it to totally cancel out, but nearby the integrator, the pole at the origin, to leave the root locus essentially untouched. And we'll talk about, we'll sort of see how that happens. So, okay, so why does the integrator affect the root locus and therefore the transient response? Adding a pole at the origin completely changes the root locus and therefore the location of the closed loop poles and therefore the transient response, because the closed loop poles, the dominant ones, are going to dominate. That is why they're called dominant, the transient response. In order to mitigate this, we place a zero near the origin, which cancels the integrator's effects on the root locus. To see this, recall that the root locus must meet the angle condition. So we're going to meditate on the figure on the next page from Nice to understand this more thoroughly. So Nice has this nice figure that shows kind of what we're talking about here. So with proportional control, we have this situation here. There is feedback, there's a gain, and if you adjust the gain, you change the location of the closed loop poles. And the open loop poles are where all of the root locus branches start, remember that, and then they go towards open loop zeros or zeros at infinity if there are no finite zeros. So we take a look at this situation. This is, say, a third order situation. The open loop poles are all on the real axis, and the root locus would be drawn as shown. Remember that the root locus has these two conditions, the magnitude condition and the angle condition. And the angle condition requires that the angles, for any point on the root locus, the angle condition must be met, and therefore the sum of these angles from the open loop poles to anywhere on the root locus must match the angle criterion. Now, if we just pop in another pole here, you're going to add a whole bunch of angle. So therefore, you can no longer have the same root locus, and that's actually what happens in this figure B. So, say we just thought that maybe PI control would work by just sticking in a gain and then dividing by S, so putting in an integrator, just naively doing that. The entire root locus changes. Notice that instead of having no locus in this region to the right of this first pole, we now have locus in between the integrator pole at the origin and that first pole. So now we've got that. The angle criterion, this theta C that's contributed by this integrator, is significant, and it moves the root locus completely. Notice that this was the point that used to be on the root locus. Now the root locus completely misses it. Okay, so we don't want that. So we are going to do a add a 0 to the numerator, right? So we stick a numerator up there, and we put that 0 close enough to this pole that it has, and recall that zeros have the opposite effect on the angle criterion. Add one, subtract the other. So if you have the opposite sign between a pole and a 0 here, as is shown right here, this angle criterion, if you make the angle approximately the same between the pole and the 0, then it has very little effect on where that root locus is. So if they're close together, then these two angles are very nearly the same, and the effect of the integrator is essentially canceled out by the 0 on the transient response, but on the steady state response, it's actually not. So that's good news. There is something that you should notice, though, however, is that we now have added an entirely new closed loop pole to this situation. So we had 3 branches before, now we have 4 branches. And that 4th branch is going to be super slow, right? The distance to the left from the origin is the decay rate. So if we put that 0 too close, it's going to be a very, very slow decay. But if we put it too far, then we're going to affect our transient response more and more. So there's a balance there. You have to kind of come up with a balance that you're comfortable with as a designer for the criteria that you want. So you might affect your transient response too much with a given pole 0, with a given 0 location. And so you might need to adjust it, but then you might end up with too slow of a response. So you've got to sort of deal with the trade-offs that could come with this. All of these methods require some sort of trade-off, and we're going to see that now as we turn to an example, but I wanted to go over, before we do, I want to go over the general design procedure for designing a proportional controller. A PI controller. So we learned the general strategy is that we're going to add an integrator into our controller, and that we're going to also stick in a 0 to counteract the transient effects of that integrator. So that's the sort of the first order approximation of what we're doing. But there's sort of a path that we are going to take as a procedure. And I give you guys, for each of these types of controllers, I'm giving you a design procedure, steps 1 through 4. This is a guideline. It works most of the time for most problems, but there are cases where it doesn't work. So you're going to have to be able to recognize why it's not working if it isn't and adjust it accordingly. And you might need to go back and start at step 1 again, or go back to step 2. Just depends. So, step 1. Design proportional controller to meet transient response specs by choosing the gain K for the dominant closed loop poles to be whatever it is. So choose your transient response specs just by adjusting the gain. Okay, and that means you're going to be moving along the root locus to the point that you think is closest to the place that you want to be transient response wise. And we'll call the real part of that negative zeta omega n, and we'll call the imaginary part omega d, the damp metric frequency. So that's where your closed loop poles are. They're on the root locus, the original root locus. Now, step 2, include an open loop integrator and 0. So the integrator always goes at the origin, so it's at s equals 0. And then a 0 at negative zeta omega n divided by 10. So essentially, we're trying to pick a number. Now, this 10 is completely, well, it's not completely arbitrary. It's a rough guideline. What it's saying is we don't want to get too close to our dominant closed loop poles with this 0. We don't want to affect the response of the system, transient response, too much. So we're going to try to pick this 0 to be on the real axis as close to the origin as is reasonable. And we're trying to sort of balance the two things. We're trying to balance the effect on the transient response, which we get as we get further away from the origin with that 0, we're affecting it more and more. And as we move it closer and closer to the origin, we have a slower and slower integral response, and that is can become very problematic if it's too slow. So this is a number to start with, so divided by 10. You might need to adjust where that 0 is to make it the version that you want. Okay. And the location of the poles is an important way to measure if it's where you want. Also, some other response characteristics as well. So maybe the transient response, maybe how quickly the steady state air is closed on from the integrator, and we're going to see that in this example that we're going to do in a minute. And then we're going to retune the gain K such that the closed loop poles are as good as possible. So we're going to try to get back to the transient response that we want. And then we're going to simulate the time response to see if it meets the specs. And then we're going to tune it accordingly. So that's sort of our general design process. It's really coming down out there. It's cool. Okay, so let's go ahead and do our example. We have, this is from Nice, problem 9.1. It says, design a PI controller to drive the step response error to 0 for the unity feedback system shown in figure 9.1. So it's just a unity feedback system, and we're going to add in a compensator here before G in a forward path. So the system operates with a damping ratio of 0.5. Compare the specifications of the uncompensated and compensated systems. So the first step, going back to our steps, is to design a proportional controller. Now they put in the K into the transfer function. I don't like that. I like to think of K as being part of the controller, so let's do that. So let's use a block diagram, and we're going to split out K to be the compensator here. So the first step we're going to do, remember, is to design the proportional controller by itself without any integral controller in it. So we need the root locus. Let's just go ahead and do a root locus sketch just to kind of get our juices flowing here a little bit. So warming up, we will draw the S-plane. And we're going to have, so the open loop system, so the forward path and the return path is the open loop transfer function. And it consists just of G. So we have S plus 1, S plus 3, and S plus 10 in the denominator of the forward path transfer function, which gives us 3 poles, okay? One at -1, one at -3, and one at -10. So I'll try to draw those in. So we have one at -1, try the green, one at -1, one at -3, and one at -10, okay? So then to do our root locus rules, the first one is always easiest. So let's do the real axis, no locus, locus, no locus, and then locus. So that's got to just go off to infinity. Okay, so we're getting somewhere. Remember that they start at the root locus starts at open loop poles and ends at open loop zeros. We have no, finite open loop zeros, so we are stuck with all zeros at infinity, which we have to find the asymptotes for. The asymptotes are, we can go through the rules to find the asymptotes, so we can find the sort of origin or vertex of all those asymptotes, which we sometimes call sigma A. It's just the average of these 3 pole locations. So we have -1, -3, -10 divided by 3, which gives -4.67. So our vertex of these asymptotes is somewhere around here, okay? And you're going to have 3 asymptotes. And if you went through and found out what those angles are, so the thetas associated with these, you're going to be at 60, 180, and then -60. So I'm going to go ahead and draw them in here. Oops. So there's this one. Then there's this one. And then there's this one. Okay, so those are the asymptotes. See that this pole is definitely going to follow that asymptote off to -infinity, and these two are going to split off the real axis, and we can find out where they split off, but I'm not going to, just for the sketch. And it's going to, probably not going to angle back like that, they're going to approach these asymptotes, so something like that. Okay, and we're designing this for a specific damping ratio. And recall that a specific damping ratio is associated with a ray that starts at the origin and goes out. So zeta equals 0.5 is associated with a specific ray. So zeta equals 0.5 might be that ray. I'm not drawing this to scale. I don't actually know which angle that is. I didn't calculate it. But we would like our closed loop poles to be at this location, and then one down here as well, matching. That's where we would like our closed loop poles to be, for the transient response to be met. And we're going to use MATLAB. Graphically, we just got a feel for it, but let's go ahead and just jump to MATLAB and do this. So let's open MATLAB. You can find this script on the web, so I'll just evaluate cell by cell. So the first part here, we have defined a system using the ZPK function. Has no zeros, has 3 poles, there they are, and it has a gain of 1. We just give it a gain of 1. We opened a figure and we placed in a root locus response. So I'm actually going to make this its own cell for now. And lo and behold, we have done well. So if we zoom in on this, where we want to be is along a specific damping ratio line, right? Going from the origin. And if you click on this, it actually has the frequency, so you do the data cursor, and then you click on it and it tells you the information there. It tells you the gain associated with that point, which is very helpful to know. That's what we want to solve for. And it tells you the damping, which is also something we're interested in, the pole location, frequency, overshoot, percent overshoot, all really useful stuff. So let's look at find damping of 0.5. So it's somewhere between these 2 points. So gain of 64 and a gain of 77, 78. So it's in between those because the damping is between 0.538 and 0.483. We want it to be 0.5. So do we just have to like guesstimate? No, we can actually do better than this. So once we've done this graph and we've seen kind of how close we can get, well, we can see, oh, it's in between these two, but we want to get more precise than that because MATLAB only plots a finite number of values. So let's close that and let's do, we know the gain's around 70, but it was too coarse. So what we do instead is we do the rlocus command again. This time we say 65 to 75 in increments of 0.1 in gain. Okay. And let's look at that, and we can see it only plotted that range of gain, and we can zoom on in if we like, and we can find ourselves a damping more precisely 0.5. So there are multiple values. It's somewhere around 73, 73.1, 73.2. So we'll call it 73. This gives the closed loop pole with the real part being, so negative 1.54. You can just read it off. It's the real axis value. You don't have to actually try to estimate, though. You can put a grid on this if you want, and that does help, but it's nice to use the data cursor to find a little bit better value. So negative 1.54 is the real part. Remember, our design rules require that we note what the real part is, because in the second step of the design rules, we are going to divide that by 10, and that's where our 0 is going to be. That's where we're going to place the 0 to counteract the effects of the pole, right? Of the integrator pole. So we'll call this our design point. We're going to put it at the real value divided by 10. Once again, just the place to start, okay? So now we can build a system model of the new open loop transfer function. So now we're going to call this system 2. We'll use the ZPK function again to create a transfer function model. Now we do have a 0, and we're going to put that 0 wherever 1/10 of this is. So at negative 0.154 is where we're going to place that 0. We're going to have a pole now at 0, which is our integrator pole. And then we're going to still have our other open loop poles, and the gain is 1. So there's our system 2. So we'll define that. If you wanted to look at system 2, in command window, you can evaluate it, and there's our transfer function. We've got our 0 at negative 0.154, and our integrator is in there now. So we are ready for step 3, which is to do a new root locus, and we're going to do the same range here because we're expecting that to have affected it too much. So we're going to try that same range of gains and see where we're at. So now notice that you've got the original poles, 3 poles, and then you've got the pole and the 0 there, the integrator, and then the other 0 we used to cancel out its effects. So let's zoom in on our little spot here again and we got to find the damping of 0.5 again, and these, so 71.7 or 71.8, either one has a damping of 0.5. So let's choose 71.8 to be the value we choose. So that is our design. We've totally defined it. We've got our new gain. Our original gain was 73. Our new gain is 71.8. We expected them to be close, but not exactly the same. So that's about right. Let's simulate and compare the proportional versus the PI. So when we do simulations and comparing with feedback control, what we typically do is we compare what we can do with a proportional gain only versus what we can do with a more complex controller. So let's do something with P, and then we'll do it with PI. So our original feedback control was just based off of sys1, which was our proportional controller, right? Our proportional controller with a gain of 73. We're going to use this MATLAB command feedback in order to calculate what the closed loop transfer function is with this sys1 system in there and k1 as the gain. So what this is, if we go back to our system, that's this closed loop transfer function from R to C. All right. So if we go from R to C, we have sys1 closed loop, and if we just evaluated this without defining or applying it to a variable or entering it into a variable, we get this as our transfer function. So its closed loop transfer function is third order, and it's got a gain of 73, we specified, and it will have a certain response characteristic. So we'll check it out and see what it does. We want to make this into a PI controller that'll get rid of the steady state error that we have. And so that's why we're doing this PI design and sys2. So we use feedback again to give us the closed loop transfer function. So you have to do is enter in what the forward path transfer function is there. This is the feedback path transfer function, which is just unity. It's just 1 in our case. There's nothing in the feedback. It's a unity feedback system. And then we'll do the step responses. But before we do, I want to go ahead and go back to our sheet here and say, okay, part C, we chose zeta equals 0.5. That was our design constraint. And then for MATLAB, we found that K had to be equal to 73, right? Now, this gives dominant closed loop poles, as we said, negative 1.54 plus or minus J 2.66. So we're going to include integrator and the 0. So the 0 is going to be at negative 1.54, the real part, divided by 10. Like I said, just to get us started on our design, which gives us negative 0.154. So our design is going to be K, some new value of K. We could use the old K and we'll probably be close, but we wanted to get the new one. We have S plus 0.154, small, divided by our integrator S. So this is our controller design, and now we just need to tweak the gain K again, right? And that was what we just did, and we got 71.8. Okay, so now all that's left is to simulate and compare these. So if we come back here, So we've got our closed loop transfer functions, and let's create a time vector. Let's go from 0 to 40 seconds in increments of 0.1 second, and we're going to take the closed loop transfer function, hand it to the step function, give it the time vector that we want to compute the step response over, and what comes out is the output 1, which is the output with system 1 for a step response. And for system 2, we can also compute the output for a step input. Okay. Now all we need to do is plot these responses. So let's plot them together on the same plot. So open a figure, plot y1, which is response to, for the proportional control, and y2, which is response for the PI control. And we'll turn the grid on, and we'll label them time for the X label, unit step response for the Y label, and we'll do a legend and label each trace, the P controller and the PI controller. So let's see what results. And what do you know? We have ourselves a P controller that has a significant steady state response error. With a unit step input, we should be seeing a unit output, but it is in fact not coming to unity. It is instead settling out at 0.71 approximately. So when we add the integrator, however, the PI controller, it responds about the same transiently, right? The same transient response, essentially that little overshoot and coming back. And then instead of settling out to a steady state error of 29%, the integrator kicks in and it brings it up to approximately 0, or 0 if you were to go to infinite time. So that is a PI controller design. And that was just sort of a first whack at it. We could loop back. We could say, okay, well, this looks okay, but maybe we want this integrator to be a little faster. It's kind of slow, right? I mean, it takes, another 20 seconds till it really gets very good after the initial response. So how do we make that faster? Well, we could play with, going back to our script, we could play with moving this 0 further to the left. Okay, if we made the 0 further to the left, then that pole, that integrator pole, is, as we increase the gain, is going to move to the left. It's going to get a larger negative, or a more negative real part, and will decay faster. So we could go back and let's just, for the heck of it, let's just say, okay, let's do our design point divided by 5. So that, oops, we'll evaluate that. And let's do our second root locus and see if we can't get back to our damping of 0.5, which we can. So a gain of 70 gets us there. So let's do that. Let's do a gain of 70. And then we could come back. I did evaluate it. Yeah. And then let's evaluate this and see. Wow, we did pretty much the same. Our transient response is about the same, but gee, we got a lot better on our integral control, didn't we? It responds a lot faster. And we can keep trying that. Maybe we'll be able to get away with an integrator, a 0 from our integrator that's even more drastic. So let's just see if we can stick it right there at the same location. Now we're expecting that we're gonna be moving this thing around quite a bit. So, did I evaluate? Okay, so we're moving things around, but let's see if we can still get our damping. Well, we can't in that range, but it looks like we need to go below 65. So let's go down to like 50. And see if we can. So that's still not there. So we need to go down even more. Let's go down to like 20. So we've got, okay. Notice one of the things that we did here. We moved that 0 out beyond this pole, which definitely changes things. So this relocus has definitely changed quite a bit. And so we might end up with something radically different with our transient response. But we are able to find a pole location that is, has our damping requirement. So let's see what it would give us. So this is a gain of 33.7. So 33.7. All right. So let's simulate it and see what it comes out to be. Now, that's pretty good. Notice it takes a little longer to settle, but it also has 0 steady state error, and it settles down quite quickly. So, it kind of depends on what you're looking for as a designer. If this is a response that you could live with, then that's great. Otherwise, you might want to go back, maybe try something else. Maybe try something more like instead of putting your 0 right there, you could maybe divide it by like 2, see if that works okay. And so you could play with that and come up with a design. Okay, so that is how to do a PI control design. It's pretty straightforward, not too bad, but it does require a lot of concepts to kind of come together to really understand it. So, and always remember when you're designing that you are kind of wandering off and doing your own thing. And nobody has ever designed for this system before, possibly, and you might have to improvise and choose your controller differently than you would by following a specific set of design rules. The 1 through 4 that I gave you they're just generally helpful to give you a first crack at it, and then you got to tweak it accordingly like we did. So, all right, well, yeah, I'll see you guys later.